All right, welcome to this explainer. If you've ever stopped to wonder how humanity actually manages to hurl massive metal tubes millions of miles across the literal void of space, well, you are in the exact right place. Today, we're going to completely demystify the physics of spaceflight and break down orbital mechanics using nothing but clear, step-by-step logic. Let's dive right in. Here's our roadmap for today. First, the negative energy trap. Second, the cannon and cosmic velocities. Third, we'll derive the escape velocity. And finally, the three laws of orbital motion.
Section 1. The negative energy trap.
So why is gravitational potential energy always negative? It's weird, right? When we hear potential energy, we usually think of it as a positive, useful thing. But in the math of gravity, it's always written with a minus sign. It kind of sounds like a paradox. I mean, how can energy be less than zero?
Well, the answer lies in how physicists define absolute freedom. Think about it. If you have two objects that are infinitely far apart, they have absolutely zero gravitational influence on each other. That state of total detachment, that is defined as zero energy. So, if zero is the absolute maximum state of freedom, anytime you get closer to a planet, you fall into an energy deficit. You are literally in debt to the planet's gravity. You're in a negative state.
Let's make this super concrete. Picture a 100-kilogram rocket sitting just 100 kilometers above the Earth. Its potential energy is essentially trapped in a massive gravity well, sitting at about negative 6.2 billion joules. To push higher, we have to fire the engines. And as the Tsiolkovsky rocket equation tells us, burning that mass creates the kinetic energy we absolutely need to overcome this well. So we add 1 billion joules of kinetic energy, and our potential energy climbs to negative 5.2 billion joules. We're moving further out. Add another billion, we hit negative 4.2. See what's happening? The rocket is slowly climbing out of a deep, invisible pit. When we finally burn enough fuel to add that full 6.2 billion joules, the potential energy hits exactly zero. Boom, freedom. The rocket is officially untethered, drifting off to infinity.
Section 2. The cannon and cosmic velocities. Okay, let's look at a classic thought experiment. Imagine a perfectly smooth, round planet with absolutely no atmosphere, so we can totally ignore air friction. Now put a ridiculously powerful cannon right on the surface, aiming perfectly horizontally. If you fire a cannonball slowly, gravity just pulls it down and it crashes. Pack in more gunpowder, shoot it faster, and it flies further before hitting the dirt. But if you shoot it just fast enough, the curve of its fall perfectly matches the curve of the planet itself. It keeps falling forever, but the ground just keeps curving out from under it.
Russian scientists at the dawn of the space age actually categorized these critical speeds. That perfect, continuous fall we just talked about, that's the first cosmic velocity, or orbital velocity. Here on Earth, that requires a speed of roughly 7.9 kilometers per second. It traps you in a closed loop, an orbit. But if you fire that cannon even faster, you hit the second cosmic velocity. At 11.2 kilometers per second, the kinetic energy is so incredibly massive that it literally rips that closed circular trajectory wide open, stretching it out into a parabola. You aren't just falling anymore, you are escaping the Earth's gravitational field entirely.
Section 3. Deriving escape velocity.
All right, let's roll up our sleeves and look at the math, starting with our launch point on the surface. We've got an object with an initial mass, let's call it little m sub o, sitting at an initial distance, r sub I, from the center of a massive planet. And our goal? We want to shoot this object so incredibly fast that it follows that red trajectory arrow right on out to the great beyond, never to return.
To actually solve this, we lean on one of the absolute most unbreakable rules in physics, the law of conservation of mechanical energy. Basically, the total energy we have at the initial launch point has to equal the total energy at the very end of the journey. The sum of our kinetic energy, our speed, and our potential energy, that gravity debt we talked about, remains perfectly constant for the entire flight.
And here is where we use a pretty brilliant physics trick. To find the absolute minimum speed required to escape, we set our final destination distance to positive infinity. And since we want the minimum launch energy, we imagine the object arrives at infinity with exactly zero speed left over. It just barely crosses the finish line. When you plug in 0 for the final speed and infinity for the final distance, the entire right side of our massive energy equation just beautifully collapses to 0.
After doing a little algebraic shuffling with the remaining terms, we get this incredibly elegant formula. The escape velocity, v, equals the square root of 2 times the gravitational constant g times the mass of the planet m divided by the radius of the planet r. Did you notice what's conspicuously missing there? The mass of the object itself. It literally doesn't matter if you're launching a feather, a 100-kilogram rocket, or a battleship. The required escape speed only depends on how heavy and how dense the planet is. Now, of course, while the speed doesn't care if you're a feather or a rocket, actually achieving that speed requires fuel. Which naturally brings us right back to the grueling realities of the Tsiolkovsky rocket equation to calculate our required fuel mass.
And when you plug the actual mass and radius of our home planet Earth into that equation, you get a very specific number, 11.2 kilometers per second. To put that into perspective for a second, that is roughly 10 times faster than a speeding bullet. That is the sheer violence, the raw energy required just to pay off Earth's gravitational debt.
Section 4. 3 Laws of Orbital Motion. So what happens once we're actually up there? Well, long before we ever had rockets, Johannes Kepler figured out the 3 rules of orbital motion just by watching the planets. First, the shape of any closed orbit isn't a perfect circle. It's an ellipse, a stretched oval shape, with the planet or sun off to one side. Second, as the spacecraft travels along this ellipse, it actually changes speed. When it swoops in really close to the planet, it speeds up. When it swings far away, it slows down. The math says it sweeps out equal areas in equal times, which is just a fancy way of ensuring energy stays conserved. And third, there's a strict relationship between the size of your orbit and how long it takes to complete it. Basically, the wider your orbit, the longer your year. And guys, these aren't just suggestions. They strictly dictate how we navigate the solar system. For example, if we want to fly to Mars, we don't just point a rocket and shoot in a straight line. No way. We use what's called a Hohmann transfer orbit. It's an elliptical path that uses these exact laws to smoothly connect Earth's orbit directly to Mars's orbit, sweeping through space with absolute maximum energy efficiency.
All right, let's conclude with something that will absolutely bend your mind. Let's jump back to our escape velocity formula for a second. V equals the square root of 2gm over r. What happens if you keep the mass of a planet exactly the same, but you shrink its radius? You make it denser, right? According to the math, as the radius shrinks, the escape velocity goes up. So, what if you shrank a planet so much that the escape velocity reached the ultimate speed limit of the universe, the speed of light?
If you plugged the speed of light into that formula for Earth, you would find a radius of exactly 9 millimeters. Let that sink in. That means if you could somehow compress the entire mass of the Earth into a sphere the size of a sugar cube, the escape velocity would equal the speed of light. Nothing, not even light itself, could escape its gravity well. You would have literally created a black hole. This incredibly specific size, it's known as the Schwarzschild radius.
Now, while our simple Newtonian algebra gave us the exact right answer for that sugar cube Earth, a truly rigorous understanding of black holes actually requires Einstein's general relativity, where gravity bends the very fabric of space-time itself. It is just incredible that simple conservation of mechanical energy can point the way to the darkest objects in the cosmos. But it does leave us with a pretty profound question. If energy is always conserved, what exactly happens to the kinetic energy of an object that falls into a place where not even light can escape?